right, so for the second half of this, we're going to do 6.2, which is on binomial probabilities. The word bi is associated with the number 2. So what this means is there are only 2 possible outcomes. For our random variable. There are 4 criteria that need to be met. There has to be a fixed number of trials. This is a predetermined amount before we start. So it can't be something like, until I get 6 yeses. That could be done in 6 people. You could ask 100 people before you get 6 yeses. So that's not a fixed number of trials. B, the trials must be independent. They can't affect each other. You can't affect the outcome of another. This happens with rolling dice, but not dealing cards. As I deal cards out, the probability of getting another card, like a card of the same suit, goes down. So the trials are not independent. This one's kind of related to what happens with C. The probabilities must be fixed. And what I mean by that is the probability can't change between trials. And D, I actually already told you D. There must be only 2 mutually exclusive outcomes. I said only 2 outcomes earlier, but they can't have anything in common. Okay, everyone got that right? Oh, this time Mateo's longer than John Luca. Y'all good?
Yeah.
Let's go back to Sarah and I. Let's do an example. Sarah and I playing rock, paper, scissors. And my random variable is the number of times I win. In 5 games. We said 5 games. That's part of this. So do I meet these criteria? A, 5 games was specified. That's a fixed number of trials. So we meet A. B, trials must be independent. What I throw one round in general doesn't affect the way I throw another round, or whether or not I win or lose, kind of thing. So yes, independent. I mean, we could go into the psychology of it and shit like that, and then you might argue no, but if I were truly, I could flip a coin, like I could roll a die to help me pick rock, paper, or scissors, then it'd be truly random. C, are the probabilities fixed? I will win 1/3 of the chance of the time, and I won't win 2/3 of the time. Now, I could break this down further. I could tie 1/3, or I could lose 1/3. But I'm tracking how many times I win. So anything that is not a win goes in the other column. Finally, D, so that makes that a yes. The probabilities are fixed each hand, each throw. D, there are 2 outcomes. I win or I don't win. This meets the criteria for a binomial probability. Everyone ready for more? Wait, that's the one writing now. If you're still, okay. So let's go over a couple examples, and I want you guys to think this out. So let's say I want to see how completing homework affects grades. I go through the grades until I find ten students current on their homework. Is this a binomial distribution? We can if you want. Okay, Theodore says yes. Let's test the 4 things. To check, test the 4 criteria. If one fails, it's not a binomial experiment. So what was A? A was fixed number of trials. Do I have that here? I don't have that, do I? I've already failed. It might be the first 10 students. Or it may take 40. So that's not going to work. I've already failed. I would argue that probably some of the other ones don't fail or don't pass either. Like independent trials, if I have brothers and sisters, like something like that, or a couple, whether they're married or just boyfriend and girlfriend, generally they're doing shit together. Or if shit goes on in the family, it's going on for everyone in the family. So it may not even be independent. But the fixed number of trials immediately fails. Let me give you another one. I roll a pair of fair dice. Ten times. And record the number of times the sum is 7. Is this binomial? Let's go through the criteria. Is there a fixed number of trials?
Yes.
Yeah, 10, right? What colors did I use for? I went green, blue, red. Blue. Are they independent trials? Yeah, rolling dice falls in this category every time. You pick them up, you throw them again. One dice roll doesn't affect the other. C. Are the probabilities fixed? Yeah, it is. There are 6 out of 36 ways to roll a 7. and 30 out of 36 ways to not roll a 7. So while they're not, so fixed is different than equal. I think that might have been what you were going with. That's what you were thinking, right?
Yeah, there's multiple ways to make a 7.
Right. There's less ways to make a 7 than there is to not make a 7. So, but we're only recording the number of 7s rolled, and we just need that probability to not change. There are 6 different ways. And finally, D, are they mutually exclusive outcomes? Yes. Rolling a 7 and not rolling a 7 have nothing in common. Those are the requirements that are specific to the binomial distribution. You still need, we still need 0 is less than P of X is less than 1, and the sum of all P of X equals 1. But we have this here. 6 over 36 and 30 over 36 are both less than 1, both greater than 0. And if you add them up, it's 36 over 36, which equals 1. So this is a binomial distribution. Every once in a while, I gotta make sure I hit record, because I fucking panic that I didn't. Not like there isn't 4 fucking semesters of this shit recorded for someone that doesn't come to class. And let's face it, there's only 11 of you guys enrolled in this class, and there's fucking 8 of you present. I know one of them lives in San Diego. So it's either they're watching the videos after I post them or something else. And she emailed me like the day before class started and said, I didn't realize this was in person. Do I need to be there? This is like, she goes to like a university, like 4-year university. She's just filling in some general ed cheap. I said, you know what? We'll arrange for a way to do your final. I'll sit on Zoom with her or something like that. I'm not gonna do that for all 40 fucking students, but for someone that is like in a rare exception like that.
What about like absences? Like, don't you get dropped after a certain number of absences?
I can drop you.
But you choose.
I choose not to. Because I don't take a roll. I haven't taken a roll, other than the first day. First day roll call I have to do because I have to drop no-shows. Mateo was a no-show, but his daddy emailed me well ahead of time.
Can't find your email.
Daddy emailed me months ahead of time and told me what was going to be the case. He couldn't find my email, but his daddy knew how to find it.
He works with that administration.
That's not an excuse. You could have asked your daddy what it was. Do you call him daddy or dad? I hope you don't call him daddy.
Neither.
No, I hope you do call him daddy, so I can pick on you.
Neither.
Papa?
Oh.
Pop. That's a good one. All right, so formula for binomial probability. Some information you need is N is the number of trials. X is the number of successes you're looking for. You're checking? And little p is the probability of success. I'll wait for you guys to write all that down because I think the formula is something to just enjoy when you're not doing anything but paying attention. You guys ready for the magic? So this is the probability that x equals a specific x value is n choose x times p raised to the x power times 1 minus p raised to the n minus x power.
Those two x's in the front, are those both little x's?
No, this is a big X. The probability that the random variable equals a specific value. So let me get look a little bit. Like x equals x, that's, if they were the same thing, that's 100%.
Yeah, that's what I was.
That's just equaling a specific value. If you wanted to say the probability that x is like greater than a certain number, then you gotta run this thing for each scenario. Each of the x's you're looking for, yeah.
What's C?
NCX is combinations, the combinatorics. This is what we went over at the end of chapter 5. I don't know about you, but fuck all that. If you had if we had 10 trials and I want to know the probability that x is greater than 3, I got to run this shit for x equals 4, 5, 6, 7, 8, 9, 10. And I got to add all that shit up. That is no bueno. So, yay for technology. In StatCrunch, all we need is n, x, and p. We need those values. And this is a little x here. We will go stats, calculators, binomial. I use an inequality symbol here. I don't know that we've gone over inequalities. Let me just run through it real quick. Let's say there's 5 trials. Let's go back to the thing with me and Sarah. 5 trials. We have the inequality symbols greater than, less than, greater than or equal to, or less than or equal to. And we know the number of possible outcomes is 0, 1, 2, 3, 4, and 5. If I say x is greater than 2, I am looking for numbers that are larger than 2 but don't include 2. That is 3, 4, and 5. So this is the greater symbol. This differs from that one. This is the greater or equal to. I still want the 3, 4, 5, but since I have the equal to, I can also count the 2. Hopefully this is a refresher for you guys. If I want x is less than 2, now I'm looking for, this is less than. The only possible outcomes for numbers that are less than 2 that are in this number range are 0 and 1. If I say x is less than or equal to 2, so this is less than or equal to, I still have the 0 and 1, but now I can include the 2. All right, we got one example. We'll do a bunch of things with that one example. And then I need to cover what mu of x, or the mean and standard deviation are for this. Is everyone ready? Okay. So let's look at an example. 35% of car owners have 3 or more cars. We sampled 20 homes to see if they have 3 or more cars. So first thing, is this a binomial distribution? Or is this a binomial experiment? A was fixed trials, and B was independent trials. Are these both met? I'm probably going too fast. Everybody's writing still. So was there a fixed number of trials? Yeah, we said 20 homes, so that's valid. Are they independent? There's no reason to think if I sampled 20 random homes that they're not, unless I just went down the street. Like if I go down the street and one of the homes has 3, I might be in a rich neighborhood and there might be more. But if I just pick random homes throughout the town and just hit 20 houses and ask. C, is the probability fixed? We said it was 35%, so yeah. D, are there two exclusive outcomes?
That there are more.
Either they have three or more, yes, or they don't have three or more, no. Yes and no, there are two outcomes, yes and no. So that one's met as well. If you say yes or you say no. So now that we've done it's a probability, we've shown that this is a binomial experiment, let's explore some probabilities. Let's explore the probability that for A, let's say exactly 5 homes have 3 or more. Now, if I were to do this by hand, this is probability that X equals 5. Well, before I continue, maybe we should identify what N, C, and P are. Or I'm sorry, N, X, and P.
Wouldn't it be 20?
N is 20. X is actually dependent on the question. Here we said 5, we gave it. So X is given here by the handwriting. What's P? 35, and we're gonna write it as a decimal, 0.35. So if we do this in the formula, we've got 20 choose 5 times 0.35 raised to the X power, which is 5. And then we have 1 minus 0.35 raised to the 20 minus 5 power. You can slowly work this shit out by hand. And you're gonna get 0.127199185. We're gonna do it in Stack Crunch. Choose 5 times 0.35 raised to the 5th power times 1 minus 0.35 raised to the 15th power. I'll do the 20 minus 5 on my own. So you can do it on the calculator, and actually plugging it in the calculator isn't too bad. As long as you don't fuck up the calculator work, it's not too bad. But you gotta remember the formula and a bunch of shit. Let's see what it looks like in Stack Crunch. Everyone ready? So we are gonna go stats, calculators, binomial. It says N is 20, that's what we had. P is 0.35. Now make sure to see we got a drop down menu here. You got to make sure you do the right drop down menu. Because we have all those inequalities we can use, or we can do exactly equals. We were looking at X equals 5. And notice as soon as I click the symbol and have the right X value in there, it immediately spits it out. I also want to point out, can you guys see that the 5 line is red? and the rest of the lines are black, it's telling me what line it's looking at. Okay? What if I wanted less than 4 homes? If I wanted less than 4 homes, that's less, and that I will just put in 4. And we're going to click compute. Now, you may not be able to see it very well, but there's a really, really small dot here for 0. Then there's a little bar for a 1. There's a red bar for a 2. There's a red bar for the 3. So it is doing 0, 1, 2, and 3. I'm going to write what I see here down on this over here. So B will be probability of less than 4 homes. Which means if I were going to do it by hand, I got to do less than 4 is 0, 1, 2, and 3. I got to, if I go by hand, I got to do each of these. That's the probability that X is less than 4. In StatCrunch, I just plug it in. I type in probability X less than 4. I tell it what N and C or N and X are, or N and B are, and it told me 0.044376. C, probability at least 1 home. Now, if you were doing this by hand, this is probability that X is greater than or equal to 1, which is probability 1 plus probability 2. And I'm not writing the X equals part just to get more writing on the page. And you gotta go all the way up to 20. Or you could work smarter, not harder, and do that whole complement rule. This is the complement of 1 minus the probability that X equals 0, which is the only one not in it. But you don't need to worry about that in StatCrunch. StatCrunch doesn't need to worry about it. StatCrunch will just tell you. So we'll go look at that in a second after you're done writing that down.
How come we don't put X equals this instead of just like 1, 2, and 3, 4?
You should put X equals 1, X equals 2, X equals 3. I verbally said I was being lazy. But these are really X equals 1, X equals 2, X equals 3, ... X equals 20. Just Hefe is lazy. Don't be like Hefe in that regard. You should be as awesome as Hefe is all the rest of it. Like, think about it. I have a master's degree in math. For most people, I am one of the scariest people on the planet. Some would even label it evil. Who studies that shit and makes it a fucking profession? That's this guy. All right, let's do it in StackCrunch. I want X's at least one, or X's at least one home. N and P never change. Once you've got them in, you only got to change the rest. And now, look at that. It's a really, really large number. 0.9998185. Now, something else this binomial calculator has is between. Look at this tab up here, between. If I click between, note that the inequalities are locked in. So we're going to do two examples of it between, but note that they have the equal sign in there. This is a locked in thing. So for the between option, NSC has probability, and then it's got a blank, less than or equal to X, less than or equal to blank. And these are set in stone. You can't change those signs. So if I say number of homes, let's say my next one is D. I think the next letter on is D. Number of homes, or probability that between 6 and 12 homes have 3 or more.
Wait, what is the, you say probability that between 6 and?
Yeah. So what numbers are between 6 and 12? 7, 8, 9, 10, and 11, right? So even though this says between 6 and 12, what we're going to enter in StackCrunch is 7 less than or equal to X less than or equal to 11. Now, if they say, like between 4 and 9 inclusive. Inclusive is like a short way of saying including 4 and 9. Then we're actually including the 4 and the 9, and we can do the full thing. But in general, you got to be careful that you're paying attention to the way it's worded. Especially on the between where you can't change the symbol. Okay, let's just look at StackCrunch real quick, get the answers. Thank you. So we had 7 and 11 for the first one. And I know you can't see me writing it down, but it's that number in that box on the right, 0.56379.523. And I'll put it back up, the page back up in a second. But I just want you to see where I'm getting them. If I do 4 and 9, I get 0.83384,381. If you're the type of person that writes down what you're doing on your homework before you enter it into the computer, which is fucking a really good way to do it, because you can go back and check your work later on and go, what did I do? Like if you're reviewing for the midterm, say, reminder, that's this week. Starting on Thursday through Sunday, you'll be able to do the midterm. Better get 5, 6, and 7 done by then.
Do we have class on Thursday still, or?
If you want to come in and ask questions, otherwise you can stay home and work on the midterm if you want. I am not lecturing on Thursday though. I will be here as long as someone gets here before 3, I'll stay here and answer questions. No one's here by 3, I'm gonna say fuck it, I'm going home. Fair enough?
So there's still class.
I'll be here, but you don't have to show up. You can stay at home and work on the midterm if you want. If you show up, you don't even have to ask questions. If you just want to show up and do homework, you do that. All right, so let me go back to this. I said the values, I showed them on the screen, but that's what I had. There's a little bit more we need to cover in this, and then we're done. So if we want the mean and standard deviation of a binomial experiment, mu of x, the mean, is n times p. And the standard deviation is the square root of n times p times 1 minus p. These are really calculator things. Let's put a nice box around that. And then when you guys are done writing, calculate for this one. Oh shit, there is a little bit more in this. My bad. So we're not almost done. We probably got another 10, 15 minutes. So for this problem we had with the cars, we had n was 20, p was 0.35. This means mu of x is 20 times 0.35, which is 7. And standard deviation is 20 times 0.35 times 1 minus 0.35. And then we got the square root in there. And if you put all that into a calculator, you get 2.13307. But this is definitely calculator work. Don't look for this shit on StatCrunch. The reason why we're gonna do the next section is because the homework probably has a question in here for it. So I wanna show you how to do it. Yep, everyone good? Okay. So this is all assuming n is large. This all assumes n is large. If n is low, there's three outcomes. If p is exactly 0.5, this is bell-shaped. It's a bell-shaped curve. And I'll show you this on StackCrunch. We can do this on StackCrunch in a second. If p is low, this is skewed right. And if p is high, this is skewed left.
So I'm guessing low is anything under 0.5 and high is anything over 0.5.
Yeah. So low meaning less, a lot less than 0.5. Now, we desire bell-shaped. When we're doing hypothesis testing, this is what we want. So if P is high, too high, so if P is high or low, how do we pick N to be reasonable? Or guarantee the bell shape? We want bell shape because we want to be able to do like the empirical rule and do some stuff quickly that way. If you got a bell shape, you can speed up hypothesis testing and shit like that pretty quick. And not necessarily even need a computer if you know it's bell shaped. All right. To do so, we will pick N such that N times P times 1 minus P is greater than or equal to 10. I'll go through some examples right now to show you. So for our first example, we'll say P is 0.21. I need N times P, which is 0.21, times 1 minus P, which is 1 minus 0.21. I need that to be greater than or equal to 10. 1 minus 0.21 is 0.79. And if I take the 0.21 and multiply it by the 0.179, I get 0.1659 times n is greater than or equal to 10. So I'm having to do a little bit of algebra here. Finally, we'll divide both sides by 0.1659. And I get n is greater than or equal to 60.277. And in this case, you should always round up to the next whole. So we want n to be greater than or equal to 61. Funnily enough, if you work this out for p equals 0.79, you get the same thing. Because we have that p and 1 minus p. The 1 minus p will turn out to be the 0.21 if I do 0.79. Let's do a quick example with the middle one, p equals 0.5. So we're doing n times p, which is 0.5, times 1 minus p, which is 1 minus 0.5. That needs to be greater than or equal to 10. If you multiply that out, it's 0.25n is greater than or equal to 10. And if you divide by 0.25, you get n is greater than or equal to 40. If n is greater than or equal to 40, you got a bell curve. Even for the, what?
Yeah.
Either way.
Nice. Arms.
You're snoring, he wakes really fast.
Oh, no, just like when.
Probably just his eyes shut, resting, listening.
I thought it was like, didn't sleep.
All right, so let me kind of show you this in StatCrunch. I think it looks, it's easier to see in StatCrunch what I mean by P is low, P is high, and how it makes that skew shape. You guys ready? Wait. Some people still right. Hold your shit, Jones. Okay. So watch what happens if I put 0.21 in. I got a hump over here on the left, and the tail on the right gets longer. And the lower I make n, the more skewed it looks. The hump is over here, and I got tails over here. But if I do 61 like we calculated, it's pretty much a bell shape. If I make the probability high, 0.9, had too many decimals there. Now it's skewed, this changes my value, 61 is kind of low. Even if I go down to 20, it'll show up even more. This is way skewed left.
Wait, did you say earlier there was 15 minutes left, or?
as soon as I'm done talking, like within 30 seconds, we'll be done.
Oh, okay.
And the lower I make this, the more skewed it looks. So like, but if P is 0.5, it looks relatively bell-shaped right away. Even at low end, it looks bell-shaped right away. But if you wanted to go by that guarantee, do n is greater than or equal to 40. I think the book might recommend 30, but there's no fucking book because they didn't do the goddamn book, it's just videos and shit. And they change it every time, so I'm going with 40. All right, that's the end of lecture. If you guys don't have any questions, you're free to go. You can get the fuck out. Or if you'd like to stay, work on homework, or have any questions, stick around.
Mr. Jones.
Does anyone have any questions? Okay, I'll hit stop record then.
Let me stop this one.